Hello, this is Captain Chaudhary. Today I'm going to speak about inclining experiment. Why the inclining experiment should be done to a ship. It is very important that the ship's light displacement as well as lightship kg is known properly, because in future whenever a ship's officer has to do kg by moment calculation, he has to have the correct displacement, correct light displacement and correct lightship kg. Otherwise all the calculations in future in respect of GM determination will be wrong. So it's extremely important that nothing less than the whole ship is inclined to witness, like what is the effect of the listing moment that is caused to the ship. A simple rule: if the GM is poor, the ship will incline more. If the GM is good, the ship will incline less. Say for example, if there is a tender ship and we fill up say number 3 starboard DB, you might have a list of something like 5 or 6 degrees. Whereas if the ship is stiff, ship's GM is good, you might have a list not more than 1.5 degrees. So lightship determination and determination of lightship kg should be done to every ship, every passenger ship and every cargo ship more than or equal to 24 meters in length. Now this kind of experiment is also required to be done where there are material changes done to the ship, and passenger ship every 5 years has to be re-inclined to do the renewal survey in respect of displacement as well as kg. The administration might dispense with inclining experiment of a ship which is one of the several sister ships which are identically built. Administration may dispense with determination of lightship kg and displacement. Also, if you have some specially built bulkers or the liquid carriers which are going to operate in fixed areas, and looking at the example of the existing similar ships, it can be shown that they will always have adequate GM, they can be dispensed. Now I'll explain you what is the principle behind inclining experiment. What is the underlying principle? So for that, let us first understand that you have a ship. This is the waterline. Here you have center of buoyancy, you might have center of gravity here. When the weight is shifted, what happens? When the weight is shifted, what happens? Parallel and proportional to the weight, G will shift to G1. But then, because you have shifted the weight on one side, the ship will get listed on that side this way. And in the final waterline, you see the sequence of drawing. In the final waterline, the new G and new B must be vertically in that line, right? New G and new B. Now, center of buoyancy of the ship will also shift in direction of the shift of these wedges, BB1. So if I draw a line parallel to it, where it meets the vertical line on the new water line, right, this should be B1. And for small angles of list, you may say that this intersection point is transverse metacenter. So you have the relationship from here that GG1 upon GM is equal to tan theta. So this is the basic principle of listing. Now what happens on the ship? On the ship, see, you selected this hold where you're going to conduct experiment. So if you have a suspension point over here, and if the deflection of the pendulum, now this pendulum could be placed in a trough of oil. The idea is when the ship is listed, the pendulum becomes vertical and you can read the graduation on the scale. This is the scale on which the graduations can be read. So this would be considered as the length of pendulum, not the actual length of pendulum, the length of pendulum which should be considered up to the scale marking. Now on the scale you can read the deflection in centimeter, and pendulum length usually is say between 4 to 6 meters. This is the oil bath. Let us say the ship's center of gravity is in this line. Over here you have the ship's center of gravity. Now, center of buoyancy of the ship may be considered as over here. If the weight is shifted on deck, this will cause the G to shift to G1. G shifts to G1. And if we assume that this was original vertical through the center of buoyancy and center of gravity, and on the new water line this is the vertical, then can we say that this is transverse metacenter, and Gg1 upon Gm is equal to tan theta. Theta is the angle of inclination. Now if you look at this red triangle and if you compare it with this white triangle, which I am going to shade now, it can be said that Gg1 upon Gm is equal to tan theta, and this is also equal to deflection in meters divided by length of pendulum in meters. But how much is Gg1? How do you get Gg1? So W, that is the weight that is shifted, and D is the distance through which the weight is shifted, divided by displacement is equal to Gg1. So when we write down this, we get W into D upon displacement into Gm is equal to deflection upon length of pendulum. Tan theta becomes independent. So what we can find out from here is the Gm. Therefore, the Gm is equal to, take everything else on the other side, W into D divided by displacement into deflection in meters into length of pendulum. So this is how we can find out the Gm at the time of experiment. Gm fluid, this would be called Gm fluid at the time of experiment. So this is the basic principle. If we know the Km at the time of experiment, from Km we can remove Gm fluid, right, to get the Kg fluid. And from the Kg fluid, if I remove free surface correction, I will get Kg solid at the time of experiment. So we will do later on a numerical to explain these facts, and with the help of numerical we will try to understand. But before that, let us try and understand formalities in respect of conducting an experiment. Index Stability Code 2008 explains the procedures and the requirement in respect of documentation, etc., to be done before the experiment. Notification to administration is important. The shipyard or the ship owners will give notification to the administration. Now, administration representative must witness the inclining experiment. In the notification, we will give a document which will explain like what kind of procedure we are going to follow, what kind of equipment we are going to use, what are the weights we are going to use. As far as preparation is concerned, the shipyard or the ship owners or the naval architect has a responsibility for the preparation. A systematic preparation would help in accuracy. So let us see what all things should be also provided along with the initial notification. So in the notification we will provide who's the person in charge of the inclining experiment. We need to tell them about the condition of the ship at the time of experiment. For example, we need to tell them what is the condition of the ship at the time of experiment. As you know, the ship should be as complete as possible, as upright as possible. We need to tell them about the tanks, like what tanks are going to be full, partly full. Those tanks which are not full or partly full, they should be left open, because we need somebody to travel to those tanks to make sure that the tanks which are empty or declared empty, they are actually empty, because we cannot afford to have any error or any mistake at this time. If a tank is empty, it has to be witnessed to be empty. Now, apart from this, the name of the ship, the description of the place where the experiment is to be conducted, what are the kind of weights we are going to use, what is the accuracy, how is the accuracy determined in respect of the weight. If the ship is going to be trimmed, if the trim is going to be excessive, it's going to impair in our stability calculation. So one should try that the trim is as less as possible. In fact, they say that the trim should not be more than 1% different than the design trim, so that the calculations are accurate. Because what happens is when you incline the ship, the profile of the change, water plane area of the ship changes. The trim also would change. At low draft, what happens is at low draft the ship is not so much wall-sided. It is more tapered towards the keel. So because of that, what happens is slight change of list or trim. There is a abrupt change of water plane area. We need to tell them as to what kind of pendulum, or if any alternative arrangement is done to the pendulum, what are these arrangements, these weights, how they are certified, how accurate these weights are, what is the provision in respect of shifting of the weight on the deck. Apart from this weight, what are the extra weights on the ship? Do you have oil, bunkers? Where are they placed? And how do you wish to determine the free surface effect of these tanks? If there are any loose weights on the ship, they have to be replaced. If there are any unwanted weights on the ship, they should be removed. If you need to shift the weight vertically or longitudinally, it should be done. The experiment should be done in the calm waters. So it may be an enclosed dock where you are conducting the experiment, or if it is outside the dock, it should be sheltered water. We cannot conduct this experiment in excessive winds and things like that. When you make fast the ship on the jetty, right, the mooring lines have to be seen. Mooring lines should not be obstructing the inclination of the ship. When the ship inclines on one side, ship should not touch on one side. It may be, more water on one side, less water on the other side, because this will hamper our calculations. So mooring lines have to be attended properly, particularly if the winds are onshore or offshore. Mooring line should be secured as much as possible to the center line of the ship and close to the water line. The weights should be such that you are able to cause 2 to 4 degrees of inclination. For the big ship, the inclination of 1 degree should be sufficient, and in case of big ship, the transfer of ballast through the DB tanks may be permitted by the administration. Usually there can be 3 pendulums. If you are using inclinometer, then it can be associated with one of the pendulums. Now pendulum length, the length of pendulum should be preferably between 4 to 6 meters, because if the length of pendulum is very short, then the deflection also will be very small. It is expected that we have a deflection of something like 15 centimeter at least. If the length of pendulum is very long, what happens is it will vibrate for a longer period. Of course, for dampening of the vibrations, we use the oil bath. So pendulum actually oscillates in oil bath. But longer the pendulum, better the accuracy. For conducting the inclining experiment, monofilament piano wire is used. Now let us look at the plans which may be of use. The lines plan, the curve of form plan, general arrangement plan, capacity plan, sounding plan, the position of draft marks plan. These are the plans which may be required. Now the equipment. The equipment, naturally you need to have accurate hydrometers which are calibrated, hydrometers for the seawater or freshwater density, and hydrometer for the liquids which are inside the tank, because that measurement also has to be done. You need a sharp pencil, you need accurate calibrator, the scales, you need thermometers, you need explosion proof testing devices. So these are the various equipment you'll be using during the experiment. Now let us look at some of the precautions which need to be taken. It is very important to determine, for finding out the displacement, lightship displacement, it is very important to read the freeboard at 5 different locations equally spaced. You need to take 6-sided drafts. You need to take the density of water, right? Density of water can be taken at 3 locations, namely forward, midship and aft from considerable depth. These readings must be taken immediately before or after the experiment, because if the density changes with the change of tide, then the experiments will not be accurate. So whatever you are doing, like draft marks, the freeboard, or the density, it should be done immediately before or after. The molded draft and dimensions should be accurately taken from the plan. So at least 2 persons should take a walk through the ship, so that they confirm that whatever has been declared and whatever weights we are considering are actually on board. For example, if there are any open tanks, they should go inside and confirm that they are empty. It goes without saying that all the enclosed spaces should be properly ventilated for the safety. Now these tanks could be deep tanks where we have liquid, or the tanks could be double bottom tanks where we have liquid. So as far as possible, we should use the tanks in pair, port and starboard. And as far as possible, if the tanks could be more or less rectangular, it would be better. These deep tanks which are filled up partly should be between 20 to 80%, and the double bottoms which are filled up should be something like 40 to 60%. This is to make sure that there is a uniform rate of change of heel because of liquid. A graph is made for listing moment and tan theta for port side as well as starboard side. So when we join these various points, it should be a straight line passing through the origin. If the line is not passing through the origin, or it is not straight, that means some error in the experiment might be there. Let us look at how these graphs should appear. Tan theta starboard, this is tan theta port, listing moment starboard, listing moment port. So this is tons meter. For the first observation which you take, the listing moment should be approximately 1/3 of the maximum. Suppose you want to shift the weight on one side, say on the starboard side, then what is the maximum distance from the center line? Say it is suppose 12 meters, so you place the weight about 4 meters from the center line. So the moment that you will cause and the tan theta, if you plot, suppose the dot comes here, this is called experiment number 1 or position 1. Thereafter, you cause the maximum starboard listing moment and see what is the list coming, and that is plotted over here. And as third experiment, you might get a point here, and then 4 could be at center. You could have the 5th point here, right? Experiment conducted for the port listing moment, and it could be 6th over here and 7th over here. So if the graph gives you a line which is straight and passes through the center, it would mean that the experiment is correct and the conditions are correct, right? So this will give you confirmation that the experiment that is conducted is done nicely. Now, instead of the curve going like this, instead of curve going along the straight line, if it turns this way, or on the port side it turns this way, this means there is excessive free surface effect. Excessive free surface effect would mean that your list is increasing, whereas you are not increasing the weights, you are not increasing the listing moment, still the list is increasing. So on the both side, the curve turning like this would indicate excessive free surface. Now it might so happen that curve is a straight line on one side, but on the other side it turns this way. It means that the vessel is grounding on one side. As the experiment is conducted on one side, the experiment gives you good results, but on the other side looks like the ship is getting aground. Whereas this is the ideal line. It might so happen that throughout the experiment, the points which you get are drifted onto one side. This means that throughout there was consistent steady wind from the port side, so that even if you have not put the weight, there is list on the starboard side. This means that throughout the experiment there was a steady wind from port side. This kind of graph could be accepted by the administration. Now sometimes it might so happen Sometimes it might so happen that for a particular weight experiment, the position of the intersection comes over here. It would indicate that for this and this observation, there was gusty wind during these two experiments. So this should be redone, right? So I hope you have understood various precautions which need to be taken to conduct inclining experiment in a proper manner. The procedure and precautions are given in Intact Stability Code 2008. Now we will do a numerical to actually understand how kg of lightship is determined. So I'll take one example from my own book for MV Alpha ship. So MV Alpha ship was floating in sea water with all compartments empty except the following: DB number 2, 200 tons, fuel oil kg 1.1 and FSM 700. And then number 3 dB, port and starboard full of ballast. Then drinking water, port and starboard 20 tons each, kg 10.5, and a total FSM of 130. An inclining experiment was carried out, a weight of 18 ton at a kg 12.2 meters, and it is shifted transversely through a distance of 13 meters. Caused a deflection of 8.5 centimeters. So a deflection is 8.5 centimeters, and the plumb is 9.2 meters in length. 9.2 is the pendulum. Calculate the GM solid and the kg of the lightship. So now, so as we know that in the inclining experiment you have a pendulum which moves on a scale. The deflection is noted down, and then at the same time you have the center of gravity which moves through a small distance G1, and then if this is the metacenter, you will find that this particular triangle GG1M is similar to this triangle involving the length of pendulum over here and deflection over here. You can say that these two triangles are similar triangle. Now we know that GG1 upon GM is equal to deflection in a meter divided by LOP, and this is equal to tan theta. But we know that GG1 is equal to W into D upon displacement. So the formula becomes W into D divided by displacement into GM equal to deflection upon length of pendulum. So we can say that the GM is equal to W D upon displacement. GM goes on the other side, deflection comes here, LOP comes over here. So let us find out the GM that is obtained like this, and as you know there is free surface active on the ship, so what we will get is the GM fluid. So we'll write the values. The weight shifted is 18 tons and it is shifted through a distance of 13 meters. Length of pendulum is 9.2 meters and deflection is 8.5 centimeters, so 0.085 meter, and we are going to write down the displacement. So the lightship is 7211.6. Then there is ballast in number 2, 200 tons. and then there is ballast in 3 port and starboard full. So 3 dB port and starboard full is 683.47, 683.47, and there is 20 tons each of fresh water in the domestic tanks, so that makes it 40 tons. So the total displacement, including the weight, we should not forget, weight is 18 tons. Let's see how much it is. Total displacement is 8153.07. So that includes the lightweight, the ballast 200, ballast 683.47, freshwater 40 tons, and the weight that is used is 18 tons. So that makes it 8153.07. So let's do the calculations. 18 into 13 into 9.2 equals, divide by bracket, that makes it 3.106. So what we have got is the GM fluid 3.106 meters. Now if you look through the tables, you will find that the km, this is like experimental displacement. 8153 is the experiment time displacement, and if you see the km for experiment time displacement, the km is 15.158, and therefore kg fluid that you will get is 12.052. As you know, free surface effect has a tendency to elevate, virtually rise the center of gravity, so kg will increase because of free surface effect. And if you want to know what is the kg solid, you will have to remove the free surface effect from this, and kg solid will be less than kg fluid. So what is the free surface effect? Double bottom to center has got 200 tons and it has got FSM equal to 700 tons meter. 3 double bottom port and starboard are full, so there is no free surface effect. And domestic water which is there in port starboard tanks, 20 tons each, total FSM is 130. So I suppose that is all the free surface moment because of number 2, there is 200 tons which was there, and because of these domestic tanks. So total FSM is 830 tons meter. Now 830 tons meter divide by the displacement gives me the free surface correction as 0.102. So kg solid will be 12.052 minus 0.102. So that is 11.95. So kg solid is equal to 11.95 meters. But please note down, this is the kg at the time of experiment. We want the kg of Lightship. Now, how to get the kg of Lightship? So what I will do is, I will do the reverse calculation to find out what is the kg at the time of Lightship. So I'll write down the table's weights in ton, kg in meters, and vertical moments. Now 8153.07 is the total displacement, and what we have got, the kg solid for the experiment time is 11.95. Now what we will do is, one by one we will remove these weights. Say for example 200 tons which was in dB to center, this had a kg of 1.1 meters. We will remove this. I'll put plus sign here, but I'll put minus sign here. And then this tank number 3 port starboard, which was full, had a capacity of 683.47, and the kg was 0.7 meter, and the domestic tanks, the 40 tons in the domestic tanks, right, had a kg of 10.5. We'll remove these things. These are the weights, and of course not to forget the 18 tons which are on deck, and that 18 ton which is on deck has a kg of 12.2 meters. We'll remove all these things, but before that let us do the vertical moment calculations. So 8153.07 into 11.95 gives me 97429. Let's forget the maybe 0.2 I will write down. 200 into 1.1 gives me 220. 683.47 multiplied by 0.7 gives me 478.4. 40 multiplied by 10.5 gives me 420. And 18 into 12.2 gives me 21.96. 219.6. So all these must be removed. All these moments must be removed. Let us do the weight calculation first. That is 8153.07 minus, in the bracket we have 200 plus 683.47 plus 40 plus 18, bracket close, gives me 7211.6. Lightship displacement. Now let's look at the moment. Gives me 96091.2. 96091.2, and this divided by the lightship displacement 7211.6 gives me 13.324. So this is the lightship kg. So this is how we find out the lightship kg. The calculations are simple, and we need to have some weight, extra weight at the time of experiment. So what we do is we find out by inclining the pendulum, right? We incline the pendulum and we know Gg1 upon Gm is equal to deflection upon length of pendulum. But Gg1 is Wd upon displacement, so we are able to find out what is the Gm which is there in the denominator. We put Gm on one side, take everything else on the other side. What we will get is the Gm fluid at the time of experiment. Now this Gm fluid at the time of experiment, we can add free surface correction to get Gm solid. We know the Km at the time of experiment from the tables, and Km minus Kg solid will give you, or Km minus Gm solid will give you Kg solid. Now this Kg solid is at the time of experiment. We need to remove all these weights which were there at the time of experiment, and when we remove these weights, what we get is the lightship displacement. And lightship displacement with the resultant residual moment will give me the lightship kg, that is 13.324 meters.